Alrighty, folks, I hope you're doing well and ready to jump into computer graphics. So let's go ahead and move in and let's see where we're at in the semester so far. And if you can believe it or not, we are in week number, well, closing up week number 5 here and into week number 6. So today's lecture, we're going to be talking about something topic known as working with a frame buffer. We've already looked at this with our software rasterizers with something called the color buffer. So we're going to learn how to work with it in OpenGL. Now, just looking a little bit more out on the schedule here, and I'll get rid of myself so you can actually see. Today is going to be our last official graded lab. Again, I might send out some materials for lab 12 or lab 13, but this will be the last graded one, so you don't have to worry about that. And then as noted in previous lectures, the final assignments are out. So A5's been pushed and A6 has already been pushed as well. Okay, and then you have your final project. So we'll wrap things up and things will come to a close relatively soon here. So again, make sure you're wrapping things up. Assignment 6 can be completed independently of assignment 5. Most folks are wrapping up assignment 6, or I shouldn't say most, but the folks who have started at 6 have usually been finishing up relatively quickly. So just something to keep in mind as you sort of strategize for the end of the semester here. The other note is I might wrap module 12 and 13 into one because the 18th is actually going to be a holiday. It's a university holiday, so we just have to respect that, and then you get a day off here for the Juneteenth holiday. Okay. Regardless, it'll be the same amount of content. Even if the videos are split up, whether for this week or next, it'll be the same amount of material. And we've actually, at this point, once we get through geometry shaders, that's as far as we usually get in a semester. So even in the compressed semester, we have made it further into OpenGL than we normally do. So you guys have been doing a really nice job and working really hard. So that's well appreciated, and it's paying off because you're going to learn some extra stuff. And which is awesome for those wanting to pursue more graphics, go on to graphics internships, co-ops, and so on. So let's go ahead and just kick off the discussion talking about frame buffers. There's a really nice reading that goes with today, and you're going to see that it goes with the lab for today as well. So, okay, to the slides. Module number 11. And a nice warm-up today is to let you know about a YouTube channel that I like. These days I really like a lot of the stuff going on YouTube. But this one's called 2-Minute Papers, and it tends to focus on applications that are graphics related most of the time. Sometimes there's AI or machine learning things, but if you take a look at this, is just what's going on right now. But all sorts of interesting sort of academic and industrial applications of research, and the theme is that it's explaining really difficult or technical material, but only in a few minutes. They're originally 2-minute papers. Now they're a little bit longer, but they're pretty cool to look at. So I'm just going to click on this one just for a moment and flip through it as soon as the ads end here, just so you can kind of get an idea of the feel for this YouTube channel here. Okay, and there we go. All right, so here's the actual paper. So it'll show you what it is, give you a little bit of a highlight, and then a few clips of it. And again, they're usually graphics related. And this is pretty cool here. I haven't actually seen this one, but anyway, you can get an idea of what's going on, some of the different and latest and greatest techniques. So some ideas for inspiration or topics that you might be interested in, or maybe last minute inspirations for your final projects. Okay, so as we're moving in to this lecture, last lecture we talked about scene trees, this data structure that allows us to organize our graphical scenes in a hierarchical manner. And we talked about how this was really, really useful because then we could do things like if we had some car and it had wheels and we wanted the wheels to move with the car, we could have a hierarchy such as the transform of your car, or if you want to think of the body of the car or the torso of the car, as it moves, the wheels should move along, okay? And that's a really nice way to organize your scenes. So you can sort of usually visualize it with this sort of scene tree here, or this view here, to see which objects are nested under each other. And it's not just limited to objects. It could be your lights, your cameras, other entities, triggers in your world, collision boxes, all sorts of things that could be in this. And that was in the first part of the lecture. And then we talked about using terrains and height fields, which is what you implemented in your lab. But again, this trick of using some texture data to lay out the terrains. And I actually want to show you something. I did a little trick here in my implementation, and just added a little bit of code so that you can actually visualize the wireframe. So if I run this and you press W, then you can actually see the wireframe, and it gives you a nice preview of what's going on here. Again, so you can see the height. Some other ideas of things that you could maybe do are, to maybe have the height map displayed instead of the color map, or be able to switch between those textures and just give you an idea of the different scene being played. So here I'm just pressing W and switching between the view there. And if you want to implement that in your terrains, I'll show you exactly where I did it here in my code. Let's see here. So I'll leave it here so you can take a screenshot or implement it, but just in the renderer function is where I have this here. So if the W key is pressed, do the line, otherwise do the fill. And you guys have been doing this as part of your assignment 3 and 4 for the wireframe views. So, but it's a nice way to debug some of the applications that we've been working on. So that's that here. And let's go ahead and move on. So again, the logistics, talked about them a little bit, but assignment 5 is out, assignment 6 is out. Remember, assignment 5 has the 2 options. I think starting with a brick wall is a great place to start. Just get the normal map working, and then you can add it to your object loader if you have time or willingness, and then otherwise to start focusing on your final projects. All right, so buffers. Today we're talking about frame buffers, and again, buffers are one of the major ideas with OpenGL and graphics. Shaders being the other, but buffers being we're storing some information somewhere and passing it along in the GPU. That information takes different forms, whether it's storing vertex information or perhaps texture information, or all sorts of other things. But today we're going to talk about a frame buffer. Okay, so again, here's some of the different ones that we've looked at: vertex buffers, index buffers, so VBOs and IBOs, or sometimes referred to as EBOs. That's something that we've looked at here. Okay, but now we're going to look at screen buffers, and in particular, what's called the frame buffer. Okay, so the frame buffer, each frame that you're drawing, when people talk about drawing a game at 60 frames per second or 24 frames per second, consists of several screen buffers: the color information, the depth information, stencil information, which we haven't talked about, but it's a way to mask away details. There can be other buffers, which I'm going to show some examples of in a commercial game. But all of these comprise and make up the frame buffer. Okay, so here's just an example of a scene here, looking at the individual buffers. So you have the color buffer on the left side. It's drawn in wireframe so you can kind of see the shapes. And then the depth buffer on the right side. So we've talked about the depth buffer where the color is describing distance. So 0 is indicated by black, 255 or 1.0 for using OpenGL coordinates would be white. So 0 to 1.0 is the range here for our depth buffer. And we can clearly see this information conveyed in each of the pictures here. Then there's also the thing called the stencil buffer, which is a way to mask away certain parts of our scene. So for instance, if we had a mirror, for example, or a reflection, or we just wanted to omit something, this is the instances where we would take advantage of this stencil buffer. So here I just have a mask, so anywhere where there's ones, it will show this part of the image here, okay? Again, why we might do that is we might only want to show a portion of a screen, or we might want part of this stencil buffer to render on top of a texture. So just this small portion, for example. If you had a small mirror object here, there's different tricks where you'd use a stencil buffer to create a mirror. Anyway, so what's the mechanism for storing these buffers? Well, these are called screen buffers. So again, we're just drawing some data as an array of pixels and then using that information to draw our final fragments in our fragment shaders, okay? And what you've noticed here is, we have color buffer and stencil buffer, or color buffer and depth buffer, but we're using that information to compose our final scene. It's breaking out the images into different screen buffers, or rather, these are separate screen buffers that we've broken out, but they will comprise of a single frame. Okay, so we can do this in OpenGL, and we use something called the frame buffer object, which you'll often see abbreviated as FBO. Okay, so we can define our own custom buffers, which is really cool. And this is where you sort of get some of the advanced sort of tricks in OpenGL to draw things in a advanced way, okay? Now you can draw whatever information you want here. You could draw the normal information, for example, from your scene and sort of render that out. That could be interesting. But you can use this as part of your graphics pipeline. And the key is the frame buffer. This is the last thing that we get in our pipeline. So again, we've been doing the fragment shader. So here's our graphics pipeline where you have your data here, you pass it in some sort of buffer here, then you send that to your vertex shader, which runs on every single individual vertex in your program, and then that's passed to the fragment shader, which is responsible for rasterizing and filling in all of your pixels. But where is it sending that pixel information to build the final image? Well, it's in the frame buffer at the end here, okay? So let me give you a little bit of a graphics study just to kind of motivate this a little bit and show you why this is cool. Okay, so again, since we're building our own pipeline, we get a lot of power here. So this is from 2016 by this gentleman, Adrian Courage, or Courage, and he's looking at the Doom 2016 game. I'm going to actually explore the log, this blog in a moment, just to see if there's anything more recent. I haven't clicked on this link in a while, but the 2016 Doom is a nice example here. Of how do they draw these highly detailed scenes. It still looks really good today, even 5 years later, for Doom. So one of the tricks is to draw these really beautiful scenes is they have these massive textures here. They're just the sort of albedo or diffuse texture maps, okay, just the color maps here, but they throw everything into these massive textures. You can see it's 16K by 8K, times 128 by 128, I guess. So, very, very big here, okay? They call it these mega textures that allocate and store all the information. And they do the same thing with all the lighting computations. So it's being stored in these massive textures here, okay? And these are being generated from the depth map, okay? And that we can get from OpenGL, which is testing how far away pixels are and storing that information into a texture, okay? And they calculate this every frame. This is where their time's spent. Now they can do other things. So this is what I wanted to show you from a commercial game, the other types of maps you can have, not just depth maps or color maps or stencil buffers or anything, but you can have a velocity map. So what this is showing is this character here who is attacking you, he jumped out from the right side. So it's mapping the little changes in the pixel, depending on the direction from each frame, and coloring those in a certain color depending on the velocity and coloring in this character here. Okay, and you can use this information to see what direction something's coming in to sort of blur this part of the image. And that's how you get a motion blur effect. You use something called a velocity map to do this. Okay, here's the depth map of that same scene, again, which we're familiar with the Z buffer. And here are some other maps, okay? The specular map. So this is just a texture map, but it colors things white. That should have a high specular component, so it's using that. And everything else is gray that shouldn't have a specular component to it. Okay, so this is how you get the sort of shimmering or metallic effect that reflects light. Okay. Now, the trend here, or what I want to show here, is just that this is all information that's being calculated every frame, and you're building it into these different maps and sort of collecting it in these separate textures. And then you're going to use those separate textures and compose them to generate a final image. Okay, and that's what you ultimately display to the user or the person who's playing this game or viewing this final scene here. Okay. All right, so let me click on that blog just because it's a little bit interesting to look at. Let's see if there's been any newer studies here. I don't know. It's always nice to look at. And he does a bunch, so you might be able to find your favorite game here. Let's see, Shadow of the Colossus. This is from the PS2, so it's a little bit older. But very beautiful game. Let's see. And it just kind of breaks down the different effects. Wow, this is pretty cool. I want to find something, though. Let's find Assassin's Creed 2. Hopefully there's nothing too crazy on here, but just want to look at this. But here's a really nice breakdown of just what's going on in the scene. Okay, so here's a scene where we can see the different diffuse map here with the color and the alpha mask, I guess, showing the transparency here. Okay, let's go ahead and close this down, look at some. So anyway, what I want you to see from this is just the different sort of layers here. Let's kind of keep going down through more. All right, so we've got some of the characters there. Well, let's try to look through some of these. The Batman game here. Let's see here. Again, you can see sort of the normal maps, the different texture maps, and so on. One other one I know is the, let me just do the Metal Gear one. This one's from a few years ago as well. But this one has a nice visualization here of just, here's the different maps that you've learned about. The color, or the diffuse map, it's referred to as albedo map. The normal map, which we looked at, the specular, and the depth. And you can just see the different components here as they're sort of put together. And what they're being put together in, and they're stored in something that's called a G buffer, where all these buffers are being generated at the same time, but they'll get composed at the end. Okay, this is a technique of generating a bunch of buffers and then deferring them, the sort of final image to the end. So anyway, let's go down here. There's another velocity map here. I'm going to scroll down a bit here. But you can kind of see how they put together the lighting here. Here's the lighting model here. They're just looking at some different things. They're really breaking this down, which is cool. You can see how the scene just sort of starts to come to life as they increase and play around with some of the lighting. So here's just the specular component, the stuff that's sort of shiny here. You can see it here on the folks. And anyway, so you have all of these final images that get combined to get you the final scene here. This one's a little bit gruesome. But anyway, the depth map composed with the albedo, the diffuse, the specular, and then SSAO is a way to do sort of shadows. You're figuring out where occlusion is, where stuff's blocked, and where a shadow would be cast. So anyway, you get the final scene there. All right, so I'll just scroll through a few of these. The base, let's see. I'm just adding some more effects here. Okay, so this is a pretty detailed, and it's a pretty well laid out presentation of this stuff. It's pretty neat how this person captures this. But anyway, this is going to be part of, there's a little optional exercise at the end of the class today to look at some actual game engines. So it's useful to look at some of these games and see, how do they compose, or what information are they capturing, so that you can get the sort of artistic or whatever the presentation is that you want. What information do you need to collect? Let me highlight the sort of most important one here. This one here, this is sort of your pipeline here. The 1, 2, 3, 4, 5 textures that get composed to this final sort of scene here, okay, to give you this effect. So if you need something else, what else can you collect? If you don't need something, what else can you get away with? We've only in this class really been concerned with the color map and the depth map, which is computed for us, okay? So anyway, nice little graphics study there, okay? Okay, so back to frame buffers and this idea. So again, our goal now, though, is to figure out how can we render some information from our scene into a separate texture? Because then we can do this sort of composition and generate some, more interesting scene potentially. Okay, so we have access to textures, right? Sampler 2Ds. We know how to get those into our fragment shaders. That's how we've been doing or drawing triangles in general onto, or drawing the textures onto our triangles from this sampler, okay? What we're going to do, though, is render our entire scene, so capture the color map into a texture, and then we can manipulate that texture in the fragment shader and create some sort of interesting post-processing effect, okay? And this is where sort of a lot of internet tutorials break down, but don't worry, we've got good support code today. So how do we create a frame buffer? Well, this is going to look familiar to the normal things we do. We're going to generate a frame buffer. So there's going to be some glgen buffers command. We're going to bind a frame buffer. So there's going to be some gl bind parentheses gl underscore frame buffer all in caps, and then you'll finally delete it later. Okay. Now there are actually going to be a few other steps in here where we're actually going to need to create a texture that we're going to be rendering to. And then we're actually going to just draw our scene on a single quad. And this is where things are a little bit weird. But we're just going to be drawing our entire scene that we'd normally be just rendering. But we're going to draw it once, capture the scene into a texture, and then redraw that texture on top of a quad. Okay. So it'll make sense when I show it, but let's talk a little bit about the frame buffer abstraction that's been added to your lab today. So today you're given a frame buffer HPPP and the frame buffer.cpp file, and this will help you create frame buffers. Okay, so let's walk through it a little bit. So you're going to have a shader associated with the frame buffer. So this is also going to be something new where we're going to have a additional shader in our lab. So you're going to have a shader for generating the scene and then another shader for doing the post-processing. So this is sort of our first use of two shaders in a program as well. And what's nice too is, anytime we want to create an object that has its own unique shader, well, we just add a shader as a member variable here, and that's a nice abstraction here. Okay, so what are we doing? Well, we got to construct the shader, okay, in our frame buffer, and then we got to do all these sort of stuff to load the shader and so on. So there's going to be a separate shader file called FBO_vert that we use here, or FBO frag for our frame buffer object fragment shader. Okay, you can name these obviously whatever you want, but this is how they are labeled today. Okay, and then you'll create the shader, and then also there's going to be another part where you're just setting up what I labeled the screen quad. So this is going to be two triangles that are laid out perfectly over the screen, okay? And this will make sense in a moment, okay? So now we need to create our frame buffer. Okay, so this is the familiar pattern where you're doing glgen frame buffers, binding it, and so on. But what's new here is we're generating the frame buffer. We're going to bind to it, but we're also going to generate a texture, okay? And this is going to be our color buffer, okay, for our frame buffer. So our frame buffer can have a bunch of things sort of attached to it, but we want to attach the color buffer to it. We're capturing the final color or output of our scene, and that's what we're drawing on a quadrilateral, okay? Some of this code is a repeat of what's in the texture code, actually, so we could actually abstract this a little bit further if I did a little bit better job here. But there's actually a function here called GL frame buffer texture 2D, which is where you attach a 2D texture with whatever your texture ID is to a particular frame buffer. Okay, there's a special function for that. Okay. Now there's a little bit here also with something called a render buffer, but we're not actually going to be using it here yet. So this is potentially for the future where we could use this, but the idea is you can generate another buffer called the render buffer, which just is a bucket of bytes, essentially, that you can render into. So if you wanted to capture multiple things or maybe manipulate pieces of data, you would use something called a render buffer for that. But a frame buffer is a thing where we can draw a texture to. So usually we just focus on frame buffers. Okay, so back to our abstraction, we have this frame buffer. Now where can we actually use it? Where can we use this frame buffer? Well, we're going to use it in our renderer, okay? So into our renderer, we're going to have an additional abstraction where we add in any number of frame buffers that we want. So I've made this a vector of pointers so we can allocate as many as we want here. We're only going to need one for our particular use case, but you might want multiple. And you might want to capture multiple frame buffers for multiple reasons. So multiple views of your scene, for instance, could be captured. So there's a few different options there. Okay. Okay, so we have to, when we're rendering our actual scene in our render, we're going to update our frame buffer, whatever it is. And by default, there's just going to be the 0th frame buffer. So that's how you're going to see it sort of labeled here. You could have 1 or 2 or however many you want, but you're going to update it, which is sort of setting the uniforms up. And then you're going to bind to that frame buffer, okay? So again, all the update's doing is it's saying, okay, bind in your frame buffer, that was this first part, and select the shader that you want, because we've got to select the pipeline that we want to be working with. So what we're going to be doing is sort of collecting this information in a texture for our scene that we are rendering to. Okay. Okay, and then once we've done that, then we render the rest of our scene here, just like normal, this part here. So if you look in your lab 10, this is going to be the same code here in lab 11, where you set up your scene, you clear it every frame, you set the clear color, you have that little wireframe trick, and then you just draw your scene tree here, starting at the root here. Okay, and then you're done with your frame buffer, then you unbind it. So you're drawing all of this here, but all this information is actually just being collected into a color map. Okay, when you draw your scene, it's drawing to our frame buffer that we have created. Okay, and then here's the magic step. So the lines after this, lines 107, 108, or whatever, here, what we do is we're done with our frame buffer, and then we say, okay, we're done with our frame buffer. So now bind to our frame buffer shader, set up our shader, and then draw the frame buffer object here, which is just a quad on the screen here. Okay, it's just 2 triangles that I'm drawing here. So here's one triangle and one other triangle here over our screen. Okay, and ta-da, you should see the same exact scene that you saw last week. But did it really work? What's going on? And it's a little bit of sorcery, because I'm going to show you what it actually looks like. The actual geometry that you're rendering is this triangle here. This is all that you're doing, 2 triangles. And you can see the actual scene here. So let me go ahead and bring this up just to show you what's going on. So let me go ahead and just open this up. And mine's a little bit modified. You'll see in a moment what we're doing here, but there's different colors. But if I hit W and do the wireframe view, you're going to notice something kind of weird. There's just like, you can see the outlines of the triangle just from this color here. And all you see here is a triangle, because we have a texture of our environments. We did the rendering step once, copied those pixels to a texture, and then we just pasted that texture over a quadrilateral. Okay, so there's no actual geometry here. It's just a texture that I'm moving around. The geometry is already rendered once. We see it, and then we just capture it as a texture and then put it on a quad. So why would we do this? You know, this sort of sorcery in a sense here, that all we're seeing is, again, yet another trick here. Well, there's a couple reasons of why, and let me get to maybe modifying the code here a little bit. If I go into the shader, let me show you what I actually did there. In the frame buffer object fragment shader, I modified this a little bit here. So instead of just outputting the fragment color here, let's see here, which was just the diffuse color, I believe. Previously, diffuse color. Let me just comment this out. Now remember, I'm working in the shader, so I don't have to recompile everything. So let's see what we get. So this time, if I run it, here we go. We get our normal, sort of texture here. But if I still, give you the wireframe view with W, it's still just a texture here. But again, the power is, let me go back into our fragment shader, comment this out, is because it's a texture, I can operate on each of the individual fragments here. And here I'm just inverting the pixel colors. So I'm just subtracting 1 minus whatever the texture is. And that gives me this totally new scene here, which is, I don't know, it's a sort of artistic effect. I don't know why you would do this in this particular scene. Maybe in a game it might be interesting, but it does give it sort of an interesting effect here. But this is a post-processing effect, and it's very efficient to do on the GPU. Our GPUs are very fast at operating on lots of pixels, and we can create this effect here, okay? So let me zoom forward just a little bit to show you, and I'll revisit those examples, what's going on here with this idea of post-processing, right? So you've probably seen post-processing, maybe if you've done photo editing where you correct someone's red eye or whatever, but that's exactly what we're doing in OpenGL, except we're just doing it in the shader, okay? So there's simple, post-processing steps you can do, like this inverting of the color here, which is what I've done here, and just flip what all the colors are. But what you can do to add some more power, and this is what you're going to be doing in your lab, is you're going to create what's called a convolution matrix, which allows you to look at nearby pixels and take some weighting of those pixels and generate a new image. So this is what's called a convolution matrix. They can be different sizes. These are 3 by 3. They could be 5 by 5 or whatever dimension you want. But if I take a weighting of these pixels, so in this one, I'm just taking whatever the current pixel I'm looking at in the middle, and then the average of the 9 pixels around, which is 0, just gives me the same image back, the identity. But if you want to do something like edge detection, you can create a 3 by 3 matrix, and you take not the color here, take the opposite colors of your current pixel. These ones, just 1 is the weighting, and then that is what you use to compute the sum of these pixels here, the weight, so negative whatever that is, negative times whatever that is, 1 times whatever the neighbor is, 1 times the top left neighbor pixel, and that is what the new center pixel color is. That's how you do an easy implementation of an edge detection. Okay, and there's various ways you can play around with this. So that's what your goal is going to be for the lab today to implement this. Okay, so here's an example from Learn OpenGL where you are taking these pixels here. So you're taking whatever your pixel color is in the middle, multiplying it by 4, the neighbors here by 2, 2 on top, on bottom, 1 to each of the sides, and then you divide whatever the result of that pixel is by 16. That's the weight here. So 2 plus 4 plus 2 plus 2 plus 1 plus 1 plus 1 plus 1 is 16. So you divide it by 16, and you're weighting the middle pixel the heaviest. That's how you get a blur. This is actually a Gaussian blur filter here, okay? And I'll actually label that a Gaussian blur because it's important. There's many different types of filters. So that's what you're going to actually implement for your lab today. And here's an example of creating that sort of blurring effect here. The OpenGL website does a nice job of doing this, but here's creating the kernel with the weightings here. Here's the different offsets here. So this is just creating the positions. So the very middle is your center. That's the current fragment that you're looking at. And the offset is just, well, minus 1 or whatever the resolution you want it to be here. In this case, they're just defining some float here. So some very small value. And then you use your kernel here to compute, so whatever this kernel is here, iterate through all the values, update your texture, or rather retrieve the values here in your sample texture, and then multiply them through your kernel, and then set that as your final color. So this is one way you can do it. You can do it more concisely if you like, but this is a nice sort of walkthrough. Okay. So here was just a simple one. I didn't actually use a kernel here, but of just inverting the colors to show the post-processing effect. Okay, and that's what you're going to be working on today. Okay, so that's your lab task, but before we get to that, let me go ahead and show you some more motivations of the frame buffer and why it's, again, useful to capture some of this information in a texture. So something that we can do is we can render a scene twice, and we can render every object in our scene twice for object selection. So what I would do is render this scene here, which is just a bunch of tiles here with this texture. But behind the scenes, I would also render each of these individual tiles again, but just as a quad and with just a color. Okay, so just using that color information. And since each of these colors are unique here that are being drawn, I can, when my mouse cursor is hovering over it, I can retrieve the information of whatever pixel my mouse is over, and look in my color buffer and figure out, okay, if it's this one, that corresponds to this particular tile. And that's one way to do object selection in OpenGL. In fact, this is a very popular strategy for doing it. Okay, other useful things are just for debugging. So this is a nice video just showing the different types of information that's being drawn here. So if you want to sort of see how your scene is, which objects are being occluded, and here's sort of separating out all the images into different screen buffers here. The diffuse colors, the edges, the depth map, and then the final scene here. And the other popular use of frame buffer objects is when you want to render a scene to a texture. So this is how you can create a reflection. So my camera, I can move my camera to wherever this object is, this quad here, render the view looking out at this direction, okay? And I just do that intermittently. Capture that as a texture, paste that texture onto my object, and move my camera back to wherever I'm supposed to be in the world here, okay? So you're rendering your scene twice, which can be very expensive to do this, but it's a way to create a perfect mirror. Okay, people will use different tricks to do that, like rendering the scene at a lower resolution, or every other frame, or things like that to get mirrors. But that's the idea here, and it's a really neat trick because graphics is full of neat tricks. Alrighty. So anyway. That's where I want to end things with frame buffer objects. So that's your lab task, to do a little bit of post-processing, and then it gives you some ideas about how some more advanced techniques like mirrors and such are implemented in graphics. An optional part, normally if we were in person, we would take part in doing this. So I'm just going to leave it as an optional exercise, if you're flying through the material and want to look at some other things, but to do a little rendering study, because we're getting to the point in the class, where we have a really nice abstraction here. And we could keep adding more components and thinking about what a good abstraction is. So I'm going to sort of zoom through this, and thinking about that Doom 2016 example I showed, or some of the other graphic studies. Normally we do sort of a breakout activity. So this is something I'll just ask you to do sort of on your own or for fun. And you can create some slides for this or whatever, but to look at actual engines, and I've listed a few here. So Horde 3D is a graphics engine, Unity 3D, Frostbite's Electronic Arts proprietary engine, Ogre 3D is an open source one. There's a nice presentation here by NVIDIA on modern engines, but to actually just look through some of these and see what goes into a modern graphics engine. What are the features? How do they do scene management? So I'm just flipping through this presentation as fast as I can so you can actually see it captured here. But just, what are the things that they think about? If I go to one of these other ones, like the Horde 3D one, you can see it there. But they've got a nice write-up just about their rendering pipeline. So again, this is the kind of stuff that can save you years by just understanding some of the trade-offs with what these engines do, rather than having to do it all on your own. This is a nice talk from again 2016 or so from EA and how they do some of their actual rendering and some of the things that they think about. And some of these really advanced engines are thinking about things at a really advanced level here. Here's the Unreal Engine. I'm going to pop this over to YouTube for a second and include this link here. This is, again, another talk here, once we get past the commercials, where they're talking about how they do all their sort of rendering here. This is with the actual developers. How they do their texturing, landscapes, collision, all these sort of things here. They have a huge Q&A. But they really do some cool tricks. I was watching just a little bit of this earlier. I'll actually just post this to the Piazza to kick off the rendering study for anybody who wants to participate in this. But this was pretty cool here. This talk about their engine, just so you can see again what the state of the art is. So let me go ahead and just paste that in here. So Nanite. Just so you can take a look at that and see where that is. Now there are a few other resources on this as well, just to talk about engines and rendering and these kind of things. Okay. So otherwise, that's all I've got for you folks here. I think there's plenty to do. I'll create that little Piazza post to kick off some discussion here. And then your task again is just to work in that fragment shader, just the frame buffer object one, to create a post-processing effect and to understand just a little bit about what frame buffer objects are doing. I highly recommend you read the Learn OpenGL page on this, just so you can know how some of the advanced OpenGL stuff works. All right, folks, so that's it for this week. Look out for the next topics. Again, next week is a holiday, so likely I'm going to there'll be like a no class thing here, and I'll move geometry shaders and just merge it in here. Geometry shaders is typically a short lecture because we're wrapping things up, but I want to combine it with at least one new topic since we've gotten further than other semesters, likely shadows, and maybe have some support code for that. So either way, you'll see these either merged into one lesson or one or the other with a little, holiday thing here. And that's it for us. All right, folks. So I will see you soon or virtually in person, and those in office hours very soon, tomorrow as of this recording. And otherwise, enjoy, keep working hard, and keep working on those final projects. I can't wait to see them. All right, take care.